Today we are going to look at properties associated with colloids. So who can remind us what a colloid was from our last class? I understand we had a 1 week break. What are these colloids? Before when we look at the properties. What are colloids by definition? Okay, I'll just call out someone from the class. I hope you received my notes. Now, you people are logging in with your registration numbers. It makes this exercise very difficult. There's Musa Nyeris Rotich. Musa, are you there?
Yes.
What do you say colloids are?
We said the colloids consist of substance dispersed in another medium.
Okay. Another try from the class. You're almost there. It's a dispersed system. Another try. We have Samuel Oginga. Samuel, are you there?
Hello?
Yes. How did you define a colloidal dispersion?
A colloid dispersion is the process whereby an insoluble substance is dispersed into another medium.
Okay. You can't remember the exact difference. Did you receive my notes? Oginga? Oginga has gone off. Okay, without wasting time, there's Amina Bashir. Amina Bashir is now a lady.
Yes.
Yeah, what was the definition of a colloidal dispersion?
It consists of a microscopically dispersed insoluble particles that are suspended throughout another substance.
You people, did you read the notes that I sent you? Amina, did you receive the notes?
We received the ones for dispersions.
Yeah, so, and those notes had the definition for colloidal dispersions. Okay, Amina, what is the size range for colloidal dispersions? Moena is off. We have Caroline Gaki. What is the size range for colloidal dispersion, Caroline?
Hello.
Yes.
From last class, you said the particle size is 1 nanometer to 0.5 micrometer.
Okay, good. Please, when you receive these notes, read them. Don't wait for the exams. Okay, today we are going to look at properties associated with colloids. So for our lecture, we look property, then at the end of it, we look at the donor membrane equilibrium effect. So those are the properties we have. Remember, we said colloids do not dialyze, but we'll see the relevance of dialysis as far as colloids are concerned. Then we look at optical properties associated with colloids, then kinetic properties, and finally the electrical properties. So dialysis, I believe this term is not new to you. You've come across it, and it normally involves a separation process based on size of molecules. Remember, we said colloidal dispersions do not dialyze through membranes. So when you have a mixture of a colloidal dispersion, small ions, the small ions will go through the membrane, depending on the concentration gradients, while the colloidal or large components will be retained. So this is just an illustration. You have your large colloidal particles mixed up with small molecules or ions. So the small molecules easily go across the membrane. And that's what we call dialysis. So at equilibrium, you'll find that you'll tend to remain with the colloidal molecules on one side, while the small ions will be distributed, will be equally distributed across the two compartments. So when you keep on replenishing the liquid in compartment B, so that you concentration gradient, you'll finally end up with your colloids in compartment A. Remember, the small ions will only dialyze when there is a concentration gradient. So when you replenish this fluid that is in compartment B, so that you reduce the concentration of the small ions in this compartment, the small ions in compartment A will go through the membrane, and eventually you'll end up with a pure colloidal solution in compartment A. So dialysis, we can use this phenomena in purification of colloids. Dialysis has also found applications in treatment of patients. And remember, we talked of blood. Blood is a colloid. The blood cells are in the colloidal size range. So we normally also apply this dialysis, especially in patients who have renal failure, kidney failure, to purify their blood, or rather remove waste products from their blood. So as your blood passes through the compartment A, the small ions that will consist of waste products or even unbound drugs will dialyze across the membrane and leave behind your blood. The blood that now will be devoid of waste products or even drugs. So these can also find applications in the medical field. So that's all we can say about dialysis. Then now we look at optical properties of colloids. Now, remember, given the particle size range of colloidal particles, they tend to scatter light. And this we described as one of the descriptions of how you can tell a colloidal solution even from a molecular solution. So colloidal solutions will tend to scatter light. And the phenomenon is known as the Tyndall effect. The light scattering is what we refer to as the Tyndall effect. And this light scattering will tend to form a cone, a beam, an illuminated beam or a cone, which also we call it as the Tyndall. A good example that maybe you've come across is the hazy illumination of a light beam from a film projector in a smoke-filled theater. Remember we said smoke is an example of a colloidal dispersion. So when you pass light through a smoke-filled theater, you'll tend to form light beams. And again, another example, dust. When you are driving along a dusty road and you have your car headlights on, the headlights will tend to come out as a beam, a Tyndall beam or a cone. So if the colloidal particles are very large, the colloid will even appear turbid in ordinary light as a result of the light scattering effect. So we'll see the relevance of this light scattering effect as far as colloidal dispersions are concerned. So this is what I'm just trying to explain, when you have your molecular solution and your colloidal solution. So if you pass a beam of light through these two solutions, in one you will see what we call the Tyndall beam or the Tyndall cone. There will be a visible beam as in a colloidal solution as compared to molecular solution. So in the lab, if you have two solutions, so in one you'll observe, in the colloidal solution, you'll observe a cone or a beam of light when the light is passed through the colloidal solution, dispersion rather. But when the light is passed through a molecular solution, there will be no beam or cone observed. And this is because molecular solutions do not scatter light because of their small size range. And this effect can be easily used to distinguish a colloidal solution from a molecular solution in the lab. You just pass a beam of light through the two solutions. So in one, you'll observe a cone or a light beam, and in the molecular solution, you won't observe anything. My slides are hanging. I don't know what is the problem. Okay. Are you able to hear me from the class? Are you able to hear me?
Yes,
Yes.
you are audible.
I am audible, eh? Okay, so we can continue. So this Tyndall effect also happens in nature, and maybe you've just come across this when sun rays pass through clouds. They also tend to form beams or cones. So this is just an illustration of the Tyndall effect, light scattering effect that also happens naturally when sun rays pass through clouds. Remember, we said clouds also form colloidal dispersion. So when sun rays pass through clouds, they tend to form cones or light beams. So the Tyndall effect is also a natural effect. So what is the application of these optical properties or the light scattering effect of colloidal dispersion? So we can use the light scattering effect, or rather the Tyndall effect, to determine the size, shape, and also molecular weight of colloids. So we have an expression that is based on the turbidity of the light scattering effect, and this turbidity is expressed as a ratio of the intensity of the scattered light to the intensity of the incident light. So at a given concentration of the dispersed phase, the turbidity is proportional to the molecular weight of the colloids, which can be obtained using this equation. So you have this equation H subscript C over the turbidity should be equal to 1 over M plus 2P subscript C. So in this case, M is the molecular weight of the colloids. So HC and BC are known, these are constants. And of course, the turbidity, you can calculate it from the ratio of the incident, intensity of the scattered light over the intensity of the incident light. So this is the expression that you're looking at. So this is the turbidity. C is the concentration of the solute of now your colloid. Concentration of the solutes in grams per centimeter cubic, the solution. I think this one you can be able to determine. M is the molecular weight in grams per mole or Daltons of your colloids. So this is what you are interested in determining. B is an interaction constant that is given, and H is an optical constant for a particular colloid. So B and H are known. So whatever that is unknown here is the molecular weight. So you can use the same expression based on the light scattering effect of colloidal dispersion to be able to determine the molecular weight of your colloid. Now we look at the other property, kinetic properties. So kinetic properties relates to the motion of your dispersed particles. Remember, your dispersed particles will be in motion in the dispersion medium, and as a result, we'll have what we call properties associated with these motions. So we have thermally induced motions, whereby we'll have Brownian motion, colloidal dispersion, diffusion of the colloidal dispersion, and osmosis. We also have gravitationally induced motions, and this will arise due to the sedimentation of your colloidal particles in solution. Last but not least, we have what we call externally applied motions, and this will arise due to the resistance to flow of your colloidal dispersion. As a result, this is what we refer to as viscosity, resistance to flow of a liquid due to an applied external stress or external force rather. So under thermally induced motions, we have Brownian motions, and this normally describes the random movement of your colloidal particles, given the small size, the 1 nanometer to 0.5 micrometer size range. Your colloidal particles tend to move randomly in the dispersion medium. Now the velocity of your particles will particle size of your colloidal dispersion. The Brownian motions will tend to be more rapid because of the high velocity. However, when you increase the viscosity of your dispersion medium, this will tend to decrease your Brownian motions, and you can do this by addition of glycerin. So increasing the viscosity of your dispersion medium will slow down your Brownian motions, while increasing or decreasing the particle size of your particles will increase the rate of your Brownian motion. The other thermally induced motion is diffusion, and this involves the movement of particles from an area of high concentration to an area of low concentration until you achieve a uniform concentration. And this diffusion is also as a direct result from the Brownian motion of your colloidal particles. The driving force for this is the concentration gradient, and it's governed by the Fick's law. I believe you've come across this law, where D is your diffusion coefficient, A is the area across which diffusion occurs, and dC dx is the concentration gradient. dC is the change in concentration with respect to distance traveled. So as a result of Brownian motions, you'll also experience diffusion of colloidal particles. Now, from this diffusion motion, you can use it to determine the molecular, not the molecular, it's the size or the radius of spherical colloidal particles using the Stokes-Einstein equation. So we have two different types of the Stokes-Einstein equations, but in both you can see there's radius, the R, which refers to the radius of the spherical colloidal particles. So even in this one, you also have the radius. Now the rest can be provided, or the rest are constants. So D is the diffusion coefficient that you can obtain from your Fick's law. Here is the Boltzmann constant. Now for this case, R is the molar gas constant that is provided. T is the absolute temperature. Now this N is the viscosity of your dispersion medium. R is the radius of the spherical colloidal particle, and N is the Avogadro's number. So having known all that, you can substitute and be able to obtain the radius of your colloidal particles. So from diffusion motion, you can be able to determine the radius and hence the size of your spherical colloidal particles. Similarly, using diffusion motion, you can also be able to determine the molecular weight of the colloidal particles using this equation. So in this equation, what is unknown is M. The rest can be provided or can be determined. So M is what is unknown. D is the diffusion coefficient. Then V with a bar, the V with a bar is the partial specific volume that is approximately equal to the volume in centimeter cubic of 1 gram of solid from density measurement. So V with a bar, you can measure it. R is the molar gas constant. T is the absolute temperature, and it's the viscosity, and capital N is the Avogadro's number. So based on this equation, you can also be able to determine the molecular weight of your spherical colloidal particles. So diffusion can assist you, diffusion motion, to determine the radius and hence the particle size, and also you can also determine the molecular weight of your colloidal particles. whereby Cg is the gram solid per liter of solution and M is the molecular weight. So by replacing C with Cgm, you can be able now to substitute and determine the molecular weight of your colloidal particles. So you can also use osmosis as a motion to be able to determine the molecular weight of your colloidal particles. Now, sedimentation, that arises due to gravity. So the velocity of sedimentation V of spherical colloid having a density P in a medium of density P naught, and the viscosity of N naught is given by the Stokes law. So you've all come across the Stokes law. So you can also use this motion of sedimentation to determine the radius and hence the particle size of your spherical colloidal particles. Remember the densities of your colloidal particles and the medium can be determined. The viscosity also can be measured, and the acceleration due to gravity is known. So you can substitute this by, once you know the velocity, measure the velocity of your sedimenting colloidal particles, you can substitute in the Stokes equation and be able to determine the radius of your spherical colloidal particles, and hence to be able to determine the size. So sedimentation as a motion can also be used to determine the particle size of colloidal particles. Now, for colloidal particles that are less than 0.5 micrometer, remember we said the size range of colloidal particles is between 1 nanometer to 0.5 micrometer. So when you have colloidal particles of less than 0.5 micrometer, you find that they tend to undergo a lot of rapid Brownian motions that tends to offset sedimentation due to gravity. So these particles do not sediment. Instead, as a result of Brownian motion, they tend to continue mixing instead. So for this case, for you to be able to determine the radius, or rather the size of spherical colloidal particles using sedimentation, you need to introduce a stronger force so that now your particles are able to undergo sedimentation. And these now you introduce what we call centrifugation. You have to centrifuge the colloidal dispersion so that your particles are able to sediment. So in this case, now when you are using a centrifuge or centrifugation, you'll find that now your acceleration due to gravity will be replaced by this W squared X. Well, okay, this is not W as such, I'm just referring it as W, but it has a name, where this is the angular velocity due to centrifugation, and X is the distance of the particle from the center of rotation. So you'll modify your Stokes equation to become this. So where V will still be the velocity, and you can see now your acceleration due to gravity is modified so that your particles are able to sediment, and as a result, you'll be able now to determine the radius and consequently the particle size of your colloidal particle. So when you have colloidal particles of 0.5 microns, you'll have to centrifuge them so that you are able to determine the radius and hence the particle size of the colloidal dispersion has to be electrically, so the net negative positive charge will tend to attract ions of opposite charge, and that is now the nitrate ions that are in solution. Trace of sodium iodide, you will find that now your colloidal particle will have a net negative charge because of the iodide ions, and because the system has to be electrically neutral, the negative iodide charge will attract now positive charge counter ions, And in this case, this will be sodium ions from the solution. So this is what I'm just trying to explain. So this is what will happen when you carry out your reaction using excess of sodium iodide charge. So on the surface of your particle, you'll have negative iodide ions. So your colloidal particles will have a net negative charge, which will attract now positive sodium ions to counterbalance the negative charge on the particle surface. This is what we call the Stern layer. We'll be looking at it later on. Now in the next layer, you'll have what we call the diffuse layer. So in the Stern layer, the sodium ions will be tightly bound to the negative iodide ions. But now in the next layer, the colloidal dispersion, which we call the diffuse layer, you find that you'll have loosely attracted sodium and nitrate ions counterbalance the charge. And finally, now in the bulk of your medium, now where the solution is, you'll have also an equal number of sodium and nitrate ions moving freely in solution to counterbalance the charge, so that your colloidal system, your colloidal dispersion is electrically neutral. So as a result of these layers, the Stern layer, the diffuse layer, is what now generates what we call the electrical double layer. So it simply describes the interactions between surfaces of colloidal particles and ions that are present in the fluid in which the colloidal particles are dispersed. So you'll have the Stern layer that is tightly bound to the particle surface, and in this case you'll find that the positive sodium ions move the particle, and we'll have now the diffuse layer. So the diffuse layer, whereby we'll find that these particles also tend to move, but rather loosely with the particle surface. And lastly, you have now the bulk of the medium, whereby now this one does not move with the particles. It's loosely bound to the negatively charged particles, but it has an equal proportion of both sodium and negative nitrate ions to balance the charge of your colloidal dispersions and therefore make it electrically neutral. So this is just another illustration of the electrical double layer. You have a negatively charged colloidal particle as a result of excess iodide ions. So the negatively charged electrical particle, colloidal particle, will attract positively charged sodium ions that will be tightly bound to the particle surface and hence move with the particle. And this is what now we call the Stern layer. Now from the Stern layer, we'll also have a diffuse layer that will consist of both positive and negative particles that will tend also to move with the particle surface as long as they are incorporated, they are within the sleeping plane boundary. The sleeping plane boundary is the boundary at the end of the diffuse layer. Now the diffuse layer also extends to the bulk of the medium, bulk of your colloidal dispersion medium. So particles that are within the boundary of the sleeping plane or the shear plane will tend to move your colloidal particles, but particles that are outside the boundary of the sleeping plane that now extend into the bulk of your medium will not move with the colloidal particles. So as I've said, you'll find that in the Stern layer, you'll have ions of opposite charge tightly bound around the particle surface and move together with the particle layer. So the potential at the Stern layer is what we call the Stern potential. So there will be a potential because of the interaction of ions. So this is what we call Stern layer. Now in the sleeping plane or the shear plane, ions within the boundary will move together with the particles, whereas ions outside the plane will not. Finally, in the diffuse layer, ions are diffused more freely around the particles, the bulk of the medium. Now, the potential at the particle surface will be the surface potential, followed by the potential at the Stern layer, which will form the Stern potential. Now, the potential at the diffuse layer, now this is the sleeping plane, is what we call the zeta potential. And we'll see how this zeta potential is responsible for the electrical properties of colloidal dispersions. So remember, the electrical double layer will arise because of the Stern layer and the diffuse layer. So you'll have two layers, which forms now the electrical double layers. You'll have two layers around your particle surface, the Stern layer and the diffuse layer, which will form the electrical double layer. So the zeta potential arising at the sleeping plane is also what we refer to as the electrokinetic potential, and is what is responsible for the electrical properties of colloidal dispersion. So it arises at the sleeping plane, the point at which the particle and associated layer move as a unit. Now it's important to note that when you increase the zeta potential, you tend to achieve what we call colloidal stability. This will cover in our next lecture. And this arises because when you increase the zeta potential, you tend to increase the charge on the particles, and therefore your particles tend to repel. The dispersion tend to be stable. So the zeta potential is also responsible for the stability of colloidal dispersions that we'll look at in our next class. So as I've already said, this is the electrical double layer, or rather the zeta potential, that accounts for the electrokinetic phenomena of colloids, or the electrical properties of colloidal dispersions. So what is this electrokinetic phenomena, or rather the electrical properties of colloidal dispersions? This normally results from movement of charged particles with respect to the dispersion medium. So the dispersed phase particles with respect to the continuous or the dispersion medium. So we have four phenomena. We have what we call electrophoresis, electroosmosis, sedimentation potential, and lastly what we call streaming potential. I believe you'll all come up across electrophoresis somewhere in your chemistry, so it should not be a new phenomenon. So what happens in electrophoresis? So electrophoresis simply involves the movement of charged colloidal particles through a liquid and an applied potential difference. So this diagram just represents this phenomenon. Now you have your negatively charged colloidal particle, colloidal soul. And when you apply now a potential difference across the tube, so you'll find that your negatively charged particles tend to move towards the positively charged electrode. So this movement is what we call electrophoresis. So you'll find that when you apply a potential difference, depending on the charge on your colloidal particles, they tend to move towards the negatively charged electrode. And we can use this phenomena in the removal of smoke from chimney gases. Remember, smoke is a colloidal dispersion. So electrophoresis can be applied to remove smoke from chimney gases. Still on electrophoresis, in this case, you can be able to determine a zeta potential represented by this symbol using this equation, whereby V is the velocity of migration of your particles, E is the potential gradient, N is the viscosity of your dispersion medium, and this symbol is the dielectric constant of your medium. Cos pi is known. So from electrophoresis, you can also be able to calculate the zeta potential of your colloidal dispersion. Now the second aspect, electrokinetic phenomena, is what we call electroosmosis. Now electroosmosis, now in this case, is the dispersion medium that moves under an applied potential difference. Your particles, dispersed phase particles, remain stationary, but in this case, the dispersion medium moves. There's a liquid that moves relative to the particles and an applied potential difference. So in this case, you'll have to immobilize your particles. So you have plug of your colloid, your negatively charged colloid. So remember, when your colloid is negatively charged, the particle surface is negatively charged, it will attract counter ions, positively charged counter ions, to balance the charge in the colloidal system so that it's electrically neutral. So it is these positively charged counter ions that move. The positively charged counter ions are in the medium, are in the liquid, so they are mobile. So it is positively charged counter ions that will move towards the oppositely charged electrodes. And as a result of this movement, you'll find that your liquid will move. Remember, the positive charge counter ions are in the liquid. So as they move, the liquid also moves. So as I've said, it will occur when a charged particle is immobilized in an electric field, then the liquid moves relative to the charged surface. So in electroosmosis, it's the liquid that moves, but in electrophoresis, it's the particles that move. So in electroosmosis, the dispersion medium that moves, whereas in electrophoresis, is the dispersed phase of your colloidal system that is moved. And this liquid movement, the dispersion, is due to the movement of counter ions towards the oppositely charged electrode. Now, it's also important to note that electroosmosis is a direct consequence of the existence of the zeta potential between the soul particles and the medium. So when the applied potential exceeds the zeta potential, you find that now your diffuse layer will be forced to move to cause electroosmosis. So we can also use electroosmosis in the removal of water from peat, which simply is a brown deposit resembling soil. Also in dewatering of moist clay and drying of pastes. The other aspect is what we call the streaming potential. Now, in streaming potential, you force a liquid to move through a plug of charged colloidal particles. So, as this diagram illustrates, you have a pump. So you force these liquids, you pump these liquids through this plug of charged colloidal particles. So by forcing these liquids to move through this plug of charged colloidal particles, you create or regenerate an electric field. There's a potential difference that is generated. So as you force your liquid to move through, you'll find that you'll generate an electric current. That's what simply is meant by the streaming potential. In this case, you force the liquids to move through a plug of colloidal particles to generate a potential difference. So this is the reverse of electroosmosis. And electroosmosis is the liquid that moves the result of an applied potential difference. But in this case, you're actually forcing the liquid to move so that you can be able to generate a potential difference. Lastly, sedimentation potential. So in sedimentation potential, also a potential difference is generated due to the movement of charged colloidal particles. As your charged colloidal particles sediment due to gravity, they tend to generate an electric field, or rather a potential difference. So this is actually the reverse of electrophoresis. Remember, in electrophoresis, your charged colloidal particles move due to an applied potential difference. But in this case, due to the movement of colloidal particles as a result of gravitational sedimentation, they generate potential difference. Now, I want to make an observation here. I've always asked this question, what are the electrical properties of colloidal dispersions? But unfortunately, students go all the way explaining how the double layer arises, how the charge on colloidal particles arises. When I ask this question, I'm just now giving you a hint. I'm just interested in the four electrokinetic phenomena: the electrophoresis, the electroosmosis, and the sedimentation potential and the streaming potential. You only need to explain that. Don't go all the way. And you know, now once a student explains that, he believes that he deserves to score highly. Yeah? This is just to make you understand how these electrokinetic phenomena arises. But when a question is asked concerning the electrical properties of colloidal dispersion or the electrokinetic phenomena of colloidal dispersion, I'm only interested in these four effects. So I've already given you some leakage. If you find such a question, don't go all the way telling me how this charge and the electrical double layer is generated. So unless there is a question, we've not gone through this summary. I'm just assuming. So this just summarizes what you've been talking about. So we have electroosmosis as an electrokinetic phenomena. So in electroosmosis, we'll have an applied potential difference, is an electric field that is applied, and there's a liquid that moves, the dispersion medium moves through porous plug. So there's a motion of liquid. Now for electrophoresis, we also have an applied potential difference, or there has to be an electric field. And in this case, it's the dispersed phase particles that move relative to the liquid. So the liquid remains stationary, but the dispersed phase particles move. So there's motion of particles. Now, streaming potential that generates a streaming current, rather. So in this case, you force a liquid to move through a porous plug of charged colloidal particles. So the driving force is a pressure gradient. Yeah? You have to create a pressure gradient, or actually you pump your liquid, you force it to move through a porous plug to generate an electric current. Lastly, the sedimentation potential. In this case, the driving force is the force due to gravity, or you can also centrifuge. Yeah? Remember, we said colloidal particles of less than 0.5 microns will not sediment. You have to force them to sediment, and in this case, you introduce a centrifugal force. So it's the dispersed phase particles that move due to the force of gravity or centrifugal force. The liquid remains stable, and as a result of this movement of dispersed phase particles, we generate potential difference. So this is still a summary of the electrokinetic phenomena. So in electrophoresis, the particle moves, the medium rests, whereas in the particles that the medium moves as a result of an applied potential difference. So it's the potential difference across the field that results in this movement. So in sedimentation potential, the particle moves, but the medium rests. Remember, the particles are sedimenting due to force of gravity. Whereas in streaming potential, the particles rest, but the medium moves. And as a result of this movement, we generate a potential difference. So unless there is a question, I'd like us to look at the last bit of today's lecture, which is the donor membrane equilibrium effect. Any question, any concern from the class? Okay, now let's look at the donor membrane equilibrium effect. So for us to understand the donor membrane equilibrium effect, you have to consider a scenario where you have sodium chloride. So we'll use sodium chloride as an example. So you'll have a semi-permeable membrane. So you'll have sodium chloride on the outside of the membrane and sodium chloride on the inside of the membrane. And together with that, you'll also have a negatively charged colloid. Remember, the colloid will not go through the membrane. But sodium chloride consists of small ions, so they can easily diffuse across the semi-permeable membrane. So you'll have so when you have your sodium chloride in solution on one side of the semifiber membrane and a negatively charged colloid together with its counter ions placed on the other side. So the sodium and chloride ions can pass freely across the membrane, but the colloidal and ionic particles, the negative charged colloidal particles, cannot go through. So the system will reach equilibrium. So this diagram was just representing the system at equilibrium. So you'll have sodium ions and chloride ions on one side, sodium ions and chloride ions on the inside side of the membrane, together with a negatively charged colloidal particle. So at equilibrium, your sodium chloride ions, the sodium and chloride ions on the outside of the membrane will balance the sodium and the chloride ions on the inside of the membrane. That is when your system will reach equilibrium. But remember, these are colloidal dispersion, or these are systems that has to be electrically neutral. So the concentration of your positively charged ions in solution on either side of the membrane must balance the concentration of your negatively charged ions. So at equilibrium, because for you to be able to achieve electron neutrality, so the concentration of your sodium ions on the outside of your membrane must also balance the concentration of your chloride ions on the outside of the membrane for your system to be electrically neutral. Similarly, the concentration of your positively charged sodium ions on the inside the membrane must balance the concentration of the negatively charged ions on the inside of the membrane. Now remember, on the inside of the membrane, you'll have both the negatively charged colloidal particle and the negatively charged chloride ions. So for you to be able to achieve electrical neutrality, the positively charged sodium ions must also balance the negatively charged colloidal ions and the negatively charged chloride ions. So you have three sets of equations: equation 1, equation 2, and equation 3. So you can take equation 2 and equation 3 and substitute it in equation 1. So you can, because now here sodium ions are equal to chloride ions on the outside, you can take equation 2, substitute it on this part. So instead of having sodium here on the outside, you have chloride on the outside here. So you'll have the chloride ions, the concentration squared there. And in this case, instead of now having a sodium ion here, you can represent it by this, the negatively charged colloidal ion concentration plus the negatively charged chloride concentration. So you end up with the mathematical equations. I hope it is clear from your side. So you end up with this form of mathematical equation that you can further simplify it and get this. We should not worry. I'll send you the notes. You can just work out this. So you end up with this equation, whereby you have the ratio of the concentration of your chloride ions on the outside, the ratio of the concentration of your chloride ions on the inside is equal to the square root of 1 plus the ratio of the concentration of your chloride ions on the inside over the ratio of your concentration of your chloride ions on the inside. So this equation will simplify to this. You can work out that mathematically. So now base this equation. You find the negatively charged colloid will tend to drive the ion of like charge. Now that is the negatively charged chloride ions outside the membrane. Will tend to drive the ion of like charge. So when you have this scenario where you have your negatively charged colloidal particle and your negatively charged chloride particles. So due to the donor membrane equilibrium effect, you find that the negatively charged colloid particle will tend to drive this negatively charged chloride particle outside of the membrane. You can see, so if this negatively charged chloride ion was to be a diffusible drug, remember drugs are also ions, then you'll find that your negatively charged colloidal particle will tend to enhance the diffusion rate of your negatively charged drug across the membrane. And as a result, you can use this donor membrane effect to enhance the diffusion of your drug across the membrane. So now we replace our negatively charged chloride ions on the outside and our negatively charged chloride ions on the inside with a diffusible drug. So for us to be able to see the effect, so we can simply now replace this ratio, the concentration of your colloid, negatively charged colloid ions, to the concentration of your negatively charged diffusible drug on the inside of the membrane. If you have a ratio of 8, then what happens to the concentration of your diffusible drug on the outside of the membrane as compared to its concentration on the inside of the membrane? So what will be the answer here? A response from the class is just maths now. If you had this ratio of the colloid to the diffusible drug on the inside of the membrane as 8, what does this ratio become? I believe you've been following. Can we have a response? Or you are typing? People prefer to type. Okay, I can see people are saying 3, which is correct. And in this scenario, when you have the ratio of the colloidal particles on the inside of the membrane to the ratio of the diffusible drug on the inside of the membrane as 99, what becomes of this ratio? The diffusible drug on the outside of the membrane to the ratio of the diffusible drug on the inside of the membrane. Then, okay, that is correct. So you can see, due to this donor membrane equilibrium effect, you tend to enhance the diffusion of a drug across the membrane. So you find that you have, in this case, you have 3, and in this case, we have 10. So your negative colloidal particles tends to enhance the ratio or the diffusion of your negatively charged diffusible drug across the membrane. So you'll find that in this case, you'll have 10 times the amount of your diffusible drug outside the membrane as compared to inside the membrane. So by increasing the amount of your colloidal particle, negatively charged colloidal particle, you tend to enhance the diffusion of your negatively charged drugs to the other side of the membrane. So you can read more about the donor membrane equilibrium effect and even its application, maybe examples of drugs that have found applications by the donor membrane equilibrium effect. So that brings us to the end of our lecture for today. Any questions, any concerns? Any questions?